Hi, welcome to Algebra 2 Common Core. Tonight in lesson number 5, we're going to do more work with the z-scores that we learned about in lesson 4. But today we're going to be using our calculator in order to be able to calculate z-score probabilities. So first of all, on our calculator, take a look. Make sure you've got your calculator in front of you because it's really important that you know how to do this on the calculator. We're going to find the variables key, and we're going to press second vars. You'll notice that above the second vars key it says DISTR. That stands for distributions. We're going to choose number 2, which is called normal CDF. What we're going to enter into the normal CDF is the lower bound, the upper bound. Then we're going to put the value for the mean, so mu, and then sigma, the standard deviation. If you've got the newer version of the calculator, the menu, the template is going to look like this. If your calculator just gives you normal CDF parentheses when you enter number 2, then you're going to have to enter the numbers like this. But notice that it's exactly the same numbers that we would be entering on the other menu if you had a newer calculator. So in both cases, you need the lower bound, the upper bound, the value for the mean, and the standard deviation. So today's lesson is just going to practice doing some examples using this normal CDF function. So example number 1 says a swimmer named Amy specializes in the 50-meter backstroke. In competition, her mean time for the event is 39.7 seconds, and the standard deviation of her times is 2.3 seconds. So the first thing we want to do is write down the information that we're given. The mean score is equal to 39.7, and the standard deviation is equal to 2.3. Find the probability that Amy's time is between 37 and 44 seconds. So we're going to start by doing this on the calculator, but then we're going to take a look at what this really looks like on our graph. So I'm going to do the steps that I just described. So I'm going to press second vars. I'm going to choose option number 2, and that will give me the normal CDF. So that's the command that we're using today, always number 2. Now the lower bound, we're going to start with our lower bound, and we want to know if she's starting at 37, that's going to be our lower bound. Going up to 44, so that's the higher bound. Then the next thing that we're going to put in is going to be our mean, so that's our 39.7. All of these numbers are separated by commas if you've got the older version of the calculator. For the newer version, you're going to put a number on each line. And then the last number you're going to put in is the standard deviation, 2.3. Now what we'd like to do is read these as percents, because we want a probability, which of course a probability could also be read as a decimal. Our calculator, when I press enter on this, my calculator gave me 0.849. So check your calculator and see if you got the same thing. So we're practicing using the calculator today, so I want to make sure that you're doing this on the calculator. Now, of course, this is going to give us the percent 84.9%. Now, let's take a look at what the graph of this would look like. So if I have my x-axis and I have my standard deviation normal bell curve, then I'm going to go ahead and say, notice again that the words normally distributed were in this problem. The mean is at 39.7. and the standard deviation is 2.3. So if I add 2.3, that's giving me a score of 42. If I add another 2.3, that's giving me 44.3. If I subtract 2.3, that's giving me 37.4. And I see that that's probably enough for me to put on to see the numbers that I'm given. So my lower bound is 37, so I'm going to say, okay, 37 would be right around here. 44 is my upper bound, so that's going to be right around here. Notice that neither of those numbers coincide with a half of a standard deviation. So it's nice that I can calculate this using my calculator. So what this number really found is the percentage of scores that are completely between those two blue lines there. So if I added together all those percentages, and again, not having those percentages, my calculator is what's doing all the work for me today, I'm getting 84.9%. That number makes sense given my picture because it does look like I've colored in 84.9% of the bell curve. Now, let's see what happens when I've got a probability like B. For B, it says find the probability that Amy's time is more than 45 seconds. So when I do my normal CDF, and again, you're going to have to enter it in the calculator as second vars and then number 2. More than 45 means that 45 is going to be my lower bound. Now I know that we want more than 45, but it's okay if we just put the number 45. Now, in order to go more than 45, that means that it can go all the way to the end of our bell curve. We don't know exactly how far that's going to go, so I'm just going to pick a really large number compared to this lower bound. So for example, I might want to pick something like 1,000. Then I put in the mean, 39.7, and then the standard deviation, 2.3. Entering that into my graphing calculator, I'm getting the decimal, 0.0106. So that's going to give me the percent, 1.06%. And again, if you think about what this would look like on our normal bell curve, here's my 39.7. If I go up one standard deviation, that'd be 42. Another standard deviation, 44.3. So I'm looking for 45, which would be over here, and everything above it, which is very, very small. So it makes sense that my answer was 1.06%. Now in part C, I made a typing error, so we're going to slightly change this question. What is the probability that Amy's time is, rather than at least 45 seconds? At least 45 seconds means exactly the same thing as part B. So I'm going to say less than 45 seconds. So we again want to do our normal CDF. This time my lower bound, since I want less than 45 seconds, I've got to go all the way down to the left side of my bell curve. So I've got to start it at 0 because that's the smallest amount of time that Amy could be swimming. We want to go up to 45, so that's the higher bound. 39.7 is the mean. 2.3 is the standard deviation. And when I press enter on this one, I'm getting an answer, I'm just looking at it on my calculator, 0.9894. So convert that over to a percent, and that's going to be 98.94%. Now think about it for a minute. What happens when you add together the answer for part B and part C? Think about why we would get that total. Let's finish part D of Amy's race here. What is the probability that Amy's time in the next race is less than 36 seconds? So let's do our normal CDF. Less than 36 seconds means we want to start at 0 and go up to 36. Our standard deviation, 39.7. Oh, I'm sorry, our mean, 39.7. And our standard deviation, 2.3. On my calculator, this gives me the answer of 0.0538. So that would be 5.4%. And again, you could draw that on your normal distribution bell curve. And right here would be my 39.7. If I go back one standard deviation, that's going to be 37.4. If I go two standard deviations, that's going to be 35.1. So I'm trying to know what happens if I go up to 36. So 36 would be right about here. So coloring all that in, that would be about 5.4% of my bell curve. Okay, let's take a look at example number 2. If the scores on a standardized test are normally distributed, really important words there, with a mean of 560, so I've got my mu is 560, and a standard deviation of 75, answer the following questions by using z-scores. So it says find the probability that a test picked at random would have a score larger than 720, and then round to the nearest tenth of a percent. So we're going to again do our normal CDF. We want larger than 720, so my lower bound is 720. Now I've got to go quite a bit higher, so I probably want to go even bigger than 1,000. I might want to go to 10,000. And then say 560 for my mean and 75 for my standard deviation. So this is a really small decimal, 0.016448. So that's giving me 1.6%. So only 1.6% of the scores would be larger than 720. Now in the part B it says find the probability that a completed test picked at random would have a score less than 500. Round to the nearest tenth of a percent. So we're going to do our normal CDF again. And less than 500 means we want to start at 0 and go up to 500 with a mean of 560 and a standard deviation of 75. And on my calculator, 0.211855. So make that a percent and round to the nearest tenth of a percent. So that should be 21.2%. Find the probability that a completed test picked at random would have a score between 500 and 600. And the next one says between 600 and 700. I want you to pause the video and enter both of these into your graphing calculator and then come back and check to see if your answer matched mine. Welcome back. Take a look at both of my setups. For part Z, I ended up with 49.1%, and for part D, I got 26.6%. So check your answers as well as what you entered into your calculator to see if we match. Let's look at example number 3. The distribution of lifetimes of a particular brand of car tires has a mean of 51,200 miles and a standard deviation of 8,200 miles. Assuming that the distribution of lifetimes is approximately normally distributed, so again, there's those important words, round your answers to the nearest thousandths and find the probability that a randomly selected tire lasts. I guess I have a little spelling error there. I should say tire lasts. So we want to start with our mean, which is 51,200, and the standard deviation, which is, of course, for this one, 8,200 miles. So for the first one, we want between 55,000 and 65,000, so it's normal CDF, going from 55,000 to 65,000 with a mean of 51,200 and a standard deviation of 8,200. So this answer turned out to be 0.2753, and we want this to the nearest thousandth, so actually we're just going to leave this as a decimal, 0.275 for our answer on that one. Now again, for parts B and part C, I want you to take a few minutes and do those on your calculator and then come back and check with my work. Checking your answers for those last two parts. In part B, I got 0.348, and in part C, I got 0.893. Now, the explanation is really the important part here. What does this mean? So explain the meaning of this probability. The probability is that 89.3%, there's an 89.3% chance that a tire selected at random would have a lifetime of at least 41,000 miles. Let's finish off tonight with this last probability. Find the probability that the lifetime of a randomly selected tire is within 10,000 miles of the mean lifetime for the tires of this brand. So within 10,000 miles means that I can either take the mean of 41,200 and be 10,000 below, which of course would give me 31,200, or I could be 10,000 miles above the mean. So if that's true, I would be at 51,200. So if we want to find this probability, we're going to do the normal CDF of the range of scores from 31,200 to 51,200, with our mean being 41,200 and our standard deviation being 8,200. So go ahead and type that into your graphing calculator. And I got 0.777, which is the percent 77.7%. So I'm 77.7% that I'm within 10,000 miles either direction, either below or above the mean. Thanks very much for learning about normal CDF today on your graphing calculator. Make sure that you have your calculator with you and charged, ready to go in class for tomorrow, so that we can practice some more of these probabilities using our calculator. Have a great night, folks, and we'll see you next time. Bye-bye.